No, so we can begin. Well, the lady also does not mind. Понятно так. No, I don't know which language to use. Okay, we have now there are time of Troitskих. You understand? Because now we have Volodya Troitsky, Vladimir, and next Friday we shall have Evgeny Troitsky. Both are excellent.
Oh, I have
Yes.
never met him.
Yes, so you will.
Okay.
Троицкий, Троицкому глаз не выклюет. So, yes, so with great pleasure I announced a talk of Vladimir. Yes, no, so please begin.
Okay, so my talk will be about orthomorphisms.
Just because to give him possibility to say good morning. That's why. So please, Volodya.
Okay, so orthomorphisms and some related classes of operators. And this will be more a review talk. So the results are mostly known, but I will present them in a slightly different perspective.
Excellent.
And the results are, well, there are many people involved in this area. I would mention Abramovich, Hitover, Depactor.
Здравствуйте.
Huismans. Wickstead.
This name I know.
So there are many people who were involved. I definitely don't claim to list. This list is not exhaustive. So, well, so through my talk, X will be a vector lattice. So again, those who have not seen this before, you can think of this as a vector space with a nice order structure. So a vector space which has an order structure. The order structure is compatible with the linear structure, and it is a lattice order. So the order is a lattice structure. Yes. So then the positive cone, so X plus stands for the positive cone.
Yeah.
The positive cone of X. We say that X is, well, generally, because it's a lattice, we know that every finite set has supremum and infimum. But infinite sets may not have supremum or infimum, but we say that X is order complete, or Dedekind complete, order complete, or Dedekind complete, if every order bounded set has supremum and infimum. And one more concept that I want to recall, the concept of an ideal. So whenever we have a vector lattice, we have a concept of a sublattice. So a sublattice is just a subspace which is closed under the lattice operation. So a sublattice is a subspace closed under the lattice operations. And by the lattice operations, I mean sup, inf, modulus, and recall that modulus is defined, modulus of X is just X sup negative X. And well, it is a standard exercise that all these lattice operations can be expressed with each other. So this means that once your subspace is closed under any of them, it is closed under all of them. So for example, if you have a subspace that is closed under the modulus, it's already a sublattice. So, and this is usually the easiest way. So you verify that your subspace is closed under modulus, undertaken modulus, then it's a sublattice. And more generally, we say that a sublattice is an ideal. So an ideal, is a sublattice which is also closed under domination. Closed under domination in the sense that if X belongs to the ideal and some vector y is dominated by x in modulus, then y is also in the ideal. And then if we have just a fixed element, so fix a positive element, and then we can consider the ideal generated by E. It's called principal ideal. The principal it's easy what it has to be. Well, you have to take everything which is dominated by E and their scalar multiples. So I sub E, this is the set of all x, such that x is dominated by some scalar multiple of E. For some, so this is an ideal, and this is the least ideal. And now we come to some non-trivial fact. So there is a theorem due to Crane and Kakutani from the 40s. Well, this, I think when I gave my previous talk, I mentioned this, but because these are important, I want to repeat this again. So it says that this ideal, this IE, may be represented as a norm dense sublattice of some CK space of continuous functions on some compact Hausdorff space. And some comments on this, some comments that when you do this, then E itself becomes constant one functions. Okay, so E becomes the constant one function. Under some minor assumptions on the space, for example, if X is a Banach lattice, not just a vector lattice, but a Banach lattice. So it's also a Banach space. Or if X is order complete, then in this representation, IE is not just a norm dense sublattice, but it's all of IE. So then we can actually do this in such a way that IE just equals CK. So this tells you essentially that your X is really saturated with copies of CK spaces. And one more comment, that if X is order complete, then this K is not just compact, but K is extremely disconnected. So this means that the closure of every open set is again open. And therefore it's also closed and open, so it's clopen. So this set has a lot of clopen sets, and whenever you have a clopen set, you have a disconnection, right? So that's why it's disconnected, because there are many ways to decompose your set into union of two open sets. Now, if you have an extremely disconnected, so this Crane-Kakutani theorem, it gives you a lot of representations from below. It says that locally, every vector lattice locally looks like a CK space. One of the big questions in the theory of vector lattices is, well, vector lattices are defined in abstract terms, but you want to have a functional representation. So you want to represent your vector lattice as a space of functions. So Crane-Kakutani theorem tells you that locally you can always do this. Locally, you can represent your vector lattice as a CK space. What about globally? Here we can also do this globally, but there is a price. So I need to introduce another notation. So again, let K be an extremely disconnected compact Hausdorff space. And I define C infinity of K. So C infinity of K, this is the space of continuous functions from K to extended reals. So I allow infinite values. I consider functions that are continuous, but I allow infinite values, but I allow infinite values on negligible sets, such that the set where f equals plus minus infinity is nowhere dense. Okay. So these are functions which are finite almost everywhere finite continuous functions. And now what is interesting that this space can be given a structure of a vector space. It's not obvious. It's not obvious because in general, how do we subtract functions with infinite values? If we have, say, two functions which both take value infinity at the same point, what would be the value of their difference at this point? But when K is extremely disconnected, then what you can do, you can first define the algebraic operations on the dense sets where the functions are finite, and then using the extreme disconnectedness, you can extend it to the whole space. So in this case, in this special case, C infinity of K is a vector space, and it's even a vector lattice. So it's a vector lattice. And now we come to another big representation theorem, this theorem due to Maeda and Akasawara. Which says that every vector lattice X, Archimedean. So I in my talk today, I only deal with Archimedean vector lattices. So through my talk, all vector lattices are assumed to be Archimedean. So every Archimedean vector lattice X may be represented as an order dense sublattice of C infinity K for some extremely disconnected K, compact topological space K. Some comments on this theorem. So order dense means that for every positive, so if you have a function in C infinity, which is positive, so which is not zero, so non-negative and not zero, then we can actually find a function in X which is not zero and sits under it. Okay. So under every non-zero positive element of the big lattice, we can squeeze a non-zero element of the smaller of the sublattice. Second comment, that if X is order complete, then it is not only a sublattice, but it is an ideal. In C infinity K. Okay, so for order complete cases, we get a better representation. The third comment is that generally, when we do this representation, constant functions need not be in X. So generally, constant functions don't have to be in X. But if X has a weak unit, E, and by weak unit it means, well, for function spaces, think of a function that is nowhere zero, almost everywhere non-zero. So weak unit means that it's positive and it is only disjoint with zero. Okay. So it is not disjoint to anything other than zero. So then we can choose our representation so that E becomes 1, becomes the constant 1 function. And in this case, X contains constant functions. Okay, so this is one side of the preliminaries. And now the other side of the preliminaries, let me mention a little bit some operator terminology. So
sorry, Archimedean means with respect to some unit, right? You fixed a unit. Is it somewhere?
Say it again.
What is an Archimedean? I mean, so for lattice. So you fixed a unit somewhere, right?
No, Archimedean just means. Let me. Okay. Archimedean means that if we have two elements and nx is less than or equal than y for all n,
I see.
then x is 0.
Okay. Yes, thanks.
So if you have a pair of elements, you cannot have one element in infinitesimal compared to another element. Okay, so now let me recall some operator terminology. So let T be a linear operator between vector lattices. We say that T is positive if T maps positive elements to positive elements. In other words, T takes the positive cone of X inside the positive cone of Y. And positive elements form a cone, positive operators form a cone in all linear operators. So, well, once we have a positive cone, we can define an order. So we can now define an order on linear operators. We just say that T is greater than or equal than S if T minus S is positive, or equivalently Tx greater than or equal than Sx for all positive X. So this way we get an order, and it's a linear order, but unfortunately it's not a lattice order. Not a lattice order. Well, you can say, well, maybe we're looking at wrong operators. So we can, instead of all linear operators, we can consider order bounded operators. So let's say T is order bounded. If it maps order bounded sets to order bounded sets, or order intervals to order intervals, you can say T of AB is contained in CD. So for every interval AB, you can find an interval CD such that T of AB. So then we can consider consider all order bounded operators. Is this a vector lattice? And now the answer is, well, there is a theorem. due to Ries and Kantarovich. Which says that if Y is order complete, then these order bounded operators under the order defined above is a vector lattice. Moreover, it is order complete. And we can compute lattice operations by so-called Ries-Kantarovich formula. So if you have an operator T, an order bounded operator, and you want to compute the modulus of T applied to some vector X, this is the supremum of modulus of T, say Tu, over all U in the interval from -x to x. So here x is positive. And it's a common mistake that you see that modulus is not computed point-wise. So like a student dream would be that the modulus of T applied to x would be the modulus of Tx. Okay, but this is generally not true, unless sometimes it is true, but generally this is not true. So of course, if there is an operator such that Tx, modulus of Tx equal, let's say operator S, such that modulus of Tx equals Sx for all positive x, then definitely we have that S is the modulus of T. But in general, the modulus of T need not be given by this formula. So generally to compute the modulus, you have to use Ries-Kantarovich formula. So now I'm more or less done with preliminaries, and now I will go to some classes of operators. But let me start with central operators. So central operators, an operator is central. So T from x to x is called central if it is dominated by a multiple of the identity. If there exists a positive lambda, there exists a positive lambda such that plus minus T is dominated by lambda I. And well, it's very tempting to say that the modulus of T is dominated by lambda I. But it's not the same, because at this stage, I don't know whether the modulus of T even exists. So here I am not even assuming that T has a modulus, because generally operators don't form a lattice. So generally an operator need not have a modulus. So by modulus of T, generally the modulus of T is defined as T sub negative T. But this only when this supremum exists. But there are situations when this supremum does not exist. Ries-Kantarovich theorem tells you that this supremum exists when the space is order complete. But here I'm not assuming anything about the space. So here I cannot assume that the modulus of T exists. And then, so this is the central operator, and I write Z of X for the set of all central operators. All central operators from X to X. So this is called the center of X. I find the notation misleading because it's not a subset of X. So the center of X is not a subset of X. So it's, and to give you some flavor, let me prove this proposition. So what are the central operators on a CK space?
Yeah.
If I have a CK space and they take an operator, a linear operator, then the following are equivalent. First, T is central. Second, T is a multiplication operator. So this means that there exists some W in C of K such that TF is just W times F. So then we say that T is MW. Okay, so it's operator of multiplication by some weight W. So central operators are exactly the multiplication operators. And there is another curious, let me add 3, I would say it's optional, but I find it interesting that T preserves zeros in the following sense, that if you have a function which vanishes at some point, then T of this function still vanishes at the same point. And the proof is very short and elegant. So let me show you the proof. It's very kind of, I know that generally it's not a good idea to present proofs in seminar talks, but I think sometimes there are exceptions. So here the proof is very short and very nice. So 2 implies 1 is almost obvious, because if you have a multiplication operator, well, TF, well, this is WF, but this is less than or equal than modulus of W, modulus of F. And this is the norm, well, the infinity norm of WF. So we get plus minus T is less than or equal than the norm of W times the identity. So every multiplication operator is naturally dominated by a scalar of the identity operator, just because we multiply by a continuous function on a compact set which is bounded. Continuous functions on compact sets are bounded. Now 1 implies 3 is also almost obvious, because, okay, if G of T is 0, and we have TF, so we know that TG, so plus minus TG is dominated by lambda G, because T is central. So this means that the modulus of TG is dominated by lambda G. And then just take the value at T. So the TG at T is less than or equal than lambda G of T, which is 0. So then TG of T must be 0. So central operators, it's clear that central operators, if you have an operator which is dominated by a multiple of the identity, it has to preserve zeros. So these 2 implications are almost trivial, and the last implication from 3 to 2. This is the elegant one. It's not difficult. So let's suppose that T preserves zeros. Suppose that T preserves zeros. We want to prove that it's a multiplication operator. Well, we have to come up with the weight. Well, but the weight, you can, if you think for a moment, you will know what weight has to be. Weight has to be T of the identity operator, right? It's like reverse engineering. If we knew that T were multiplication operator, then we would have W equal T of 1. Okay, so we need to prove we will prove that T is multiplication by W. Well, take any G, fix K, fix point, put G of T, just denote this by alpha. And then observe that if I consider the function G minus alpha constant 1, okay, well, then this function, just by the way I defined it, when I computed the T, it gets G of T minus alpha, so this is 0. So this is 0. And now, since T preserves zeros, so by the assumption, T of this function must still have 0 at t. Okay. But now if I expand this, then I get that Tg of t is alpha times T1 of t. And now, well, T1 is W, so it's W of t, but alpha is nothing but G of t. So it's G of TW, so that's what I got. So Tg equals GW. We are done. So the proof, as you see, it's a short and elegant proof.
Yes.
And it tells me that, but the bottom line is that central operators are exactly the multiplication operators. And from this, I can get an easy corollary that what is the center of CK? Well, every central operator on CK is a multiplication operator. Okay, I have this T from the center. I know that this T is nothing but MW for some W in CK. So every multiplication operator is determined by a function, and every function gives me a multiplication operator. So this gives me just a one-to-one bijection between the center and CK itself. So the center of CK is lattice and algebraically isomorphic to CK itself. But now this is not a big deal, but what is a big deal is the following theorem, which says that for every vector lattice X, its center is a vector lattice. And now the proof, now look at the proof. The proof is very enlightening here. So we take T in the center. So we take a central operator and we pick a positive element in our space. Now I consider the ideal generated by this operator. And it's clear that central operators, just by the way, that if I should have mentioned this before, let me mention this before. Central operators preserve ideals. So T of J is contained in J, just because of the definition of central operator, because central operator is dominated by the identity, so it respects domination. So then I can consider the restriction of T to this ideal. So I can consider T as an operator from IX to IX. But IX can be realized inside some CK space.
Yeah.
And then by density, I can lift T to an operator on CK space. So on CK, we can represent T equals just multiplication operator by some W. And now when I apply, say, T to X, if I take the modulus of Tx, well, this is just the modulus of Wx, which is modulus of W. Let's say X is positive, just to make life easier. So I take a positive X. Okay, X is positive. So I am fine. So then this is modulus of W times X, which is just multiplication by the modulus of W times X. So now this means that I can represent the modulus of Tx as some operator applied to X. So then this means that T has a modulus. Equals this. So T modulus of T exists. It exists on the ideal, and therefore it exists everywhere. It exists on the whole space. So this finishes the proof. And more than that, so not only we prove the theorem, so we prove the theorem essentially by reducing it to multiplication operators, but we also show that in this case, the modulus of T is given pointwise. So it is really modulus of tx is modulus of tx. So here x is positive. So this is the student dream, that we don't need Risk-Kantorovich for central operators. When we compute the modulus of a central operator, we don't need Risk-Kantorovich. We can compute modulus pointwise.
Okay.
And in this case, once we know that, so we know that the center is a vector lattice, and every element in the center is dominated by a multiple of the identity, just by definition of central operators. So this means that if I consider the ideal generated by the identity operator in the center, I just get the whole center. So by Crane-Kakutani, the center can be realized as a CK space. Algebraically and lattice, so it's lattice and algebraically isomorphic to a CK space. So the center of a vector lattice has a very kind of natural and simple structure. Okay, let me go on. So let's go to the next class of operators, orthomorphisms.
Well, in this case, the unit is a strong unit, right?
Yes, yes, yes. In this case, I is a strong unit.
Good.
Strong unit in Z of X. And this allows us to put a Banach lattice structure on Z of X.
Could you please, concerning the K, where did it come from? Is that sort of states of the X or?
Well, this K comes from Kakutani-Crane theorem, and in Kakutani-Crane theorem, it is reduced to Stone representation theorem for Boolean algebras.
I
So
see.
basically, you start with your vector lattice, it gives you some natural Boolean algebra, and then you represent this Boolean algebra as a Boolean algebra of subsets of some compact K. So that's where this K comes from. So ultimately, it comes from the Stone theorem.
I see. Okay, thanks.
So it's not a nice. Usually, in most applications, this K would be disconnected, highly disconnected.
Okay.
Okay, so orthomorphism. So before I define an orthomorphism, let me recall what's a band. It's not critical, but it helps. So by a band is an order closed ideal. And what I mean by order closed, I mean that if you have a net in the ideal which converges, let's say, which has supremum is X, then X is also in the ideal. So it's closed undertaken supremo of monotone nets. Or equivalently, this means, let me call it B. So B, a band B. So B is the disjoint complement of some set. And by disjoint complement, I mean all X which are disjoint to everything in A. Well, a typical example, say if you take LP space on some measure space, and if you take a subset of your measure space and you consider all the functions that are supported on this subset. So this is a band. Okay. All functions, so if A is contained in your omega, then LP of A is a band in LP of omega. So we say that an operator T from X to X is band preserving. if it preserves bands, if T of B is contained in B for all B. But fortunately, if you don't like this concept of a band, you don't need it, because this is equivalent. There is a very simple equivalent characterization. Equivalently, if you have two disjoint vectors and you apply T to one of them, they are still disjoint. So T is band preserving if and only if T preserves disjointness when you apply it to one component, one of the factors. So then you can forget about bands. You don't really need to know anything about bands. You can just use this later definition. And generally, band preserving operators need not be order bounded. But we define an orthomorphism is band preserving and order bounded. So we have this chain. We have central. Well, every central operator, as we know, is ideal preserving. Every ideal preserving is obviously band preserving. And now if we restrict to order bounded, then we have orthomorphisms. So we have this chain. So orthomorphisms, they are these extra assumptions of order boundedness. It makes the class of operators much nicer. It makes the class much nicer. And now let me start with a theorem that, from my perspective, tells you really what orthomorphisms really are.
I'm sorry, your bands, they're not complemented, right, in general? I mean, they don't have complement ideal, or they should have.
Generally, no. Generally, band does not
yeah.
have to be
But
complemented.
I guess if it's complete, then that's the case, right?
Yes, if your vector lattice is complete, if X is complete.
I see, yeah. But then your band preserving operator is just sort of decomposable, right? You're gonna have a like diagonal, like sort of.
What?
I mean, if then in this case, so band preserving means it leaves invariant both of them, is it?
Yes, then it leaves invariant all of them, right?
I see. Okay.
Right.
So sort of decompose like that. Okay.
Yes, so it has a lot of it decomposes, but you will see in a moment it's much better.
Okay.
It's much better. So let X be a vector lattice. And T is an orthomorphism on X. Suppose that I embed X in C infinity K as in Maeda-Ogasawara theorem. Then T is a multiplication operator. So T, then there exists
function
W in C infinity K such that T of F equals WF for all F in X. So T is, so orthomorphisms are exactly multiplication operators on C infinity K. So orthomorphisms on X are precisely the multiplication operators on C infinity K that leave X invariant. So this gives you a really like natural, concrete representation of orthomorphisms. And in particular, if, as I say, when you do this Maeda or Ogasawara representation, constant functions do not have to be there. But if they are there, so if one is an X, then clearly this W would be T of one. And in particular, W is itself an X. In general, we can only say that W is in C infinity K, but in this special case, W belongs to X. And now we can deduce from this big theorem, which is due to, well, it's an old theorem originally due to Keimel, Conrad, and Diem. And they originally proved it in a slightly general setting. But the fact is that orthomorphisms form a vector lattice.
Mm.
Orthomorphisms form a vector lattice with pointwise lattice operations. So you don't need Risk-Kantorovich. And the proof is pretty much the same as we did for central operators. So again, we just consider T as a multiplication. So let T be an orthomorphism. Let W be as above. And then for every X, we know that the modulus, okay, for every positive X, the modulus of Tx, this is just Wx, this is modulus of Wx, and this is Mwx. So this means that there is a positive operator which satisfies this property. So this means that modulus of T exists and equals Mw, modulus of W. That's pretty much the end of the proof. Here it's not that I'm cheating, but historically, I understand that historically it happened in the opposite order. So first, these people introduced the concept of an orthomorphisms, and they introduced it even in a slightly different setting of lattice-ordered groups. And then they proved this theorem using completely algebraic means. So just using identities, various inequalities, so it like you have pages and pages of computations. But now, later, it was observed that orthomorphisms have this nice representation that orthomorphisms can be represented as multiplication operators. But now we can go backwards. We can start with say, well, let's first prove that orthomorphisms are multiplications, and this does require some work. This is, you see, I didn't show you the proof of this theorem. So this theorem, the proof of this theorem is somewhat technical. So, but once we have this representation, from this representation, we can now easily deduce all properties of orthomorphisms. Like, for example, we can now easily deduce that every two orthomorphisms commute. Well, just because orthomorphisms are multiplication operators, and multiplication operators obviously commute. We just have functions. And also, if X has a weak unit, then as I already said, we can choose our representation in such a way that one belongs to X, then this W belongs to X, and then we can actually, so this means that this multiplies itself in X. So in this case, orthomorphisms of X embed into X. So we can embed the orthomorphisms into X.
Yes.
But generally we can always embed orthomorphisms into the C infinity.
Hmm.
So in this nice case, we can embed orth into X itself, but we always can embed orthomorphisms in C infinity, and this embedding is both a lattice and algebraic embedding. And now I will mention a big and difficult theorem, but definitely the proof would take very long time. That on a Banach lattice, so if X is a Banach lattice, then all these classes of operators agree. Then central are the same as orthomorphisms, the same as band preservers. Now I think I will skip a little bit. Okay, so the next class of operators, how much more time do I have? What's the?
It depends on you.
Well,
When you will feel that you said.
no, but how much would you be willing to listen?
No,
5, 10, 15, 20,
whatever,
30?
whatever, Volodya. We are in your disposition.
Okay, so then maybe 15 or 20 more minutes.
Okay, that's very good.
Okay, then I will mention this interesting application that we have this concept of an F algebra. So an F algebra is a vector lattice, which is also an algebra. Such that it satisfies two conditions. First, the product of two positive elements is positive. And second is that it respects disjointness. So if X is disjoint with Y, then if you multiply Y on the left or on the right, you still have disjointness. Well, this condition essentially means that multiplication operators left and right multiplication, are band preserving. And you can show that they're actually orthomorphisms. So now there is a theorem which goes back to Amemia, that every F algebra is commutative. This is not difficult. I don't want to go into details, but it's not a very difficult theorem. But in particular, this means that we can talk about left multiplications and right multiplication operators. They are the same. So now from this previous, combining this and doing some extra work, we get a theorem which is due to Zaanen, that if we have an F algebra, so let X be an F algebra, with a multiplicative unit. Then the map that you take an element of X and send it to the multiplication operator by X. And we know that this is an orthomorphism. So this map is a lattice and algebraic isomorphism. So for F algebra, every F algebra can be realized and as its own orthomorphisms. But now what we already know from the previous, we know that this can be embedded into C infinity of K for the appropriate K. So this gives me another representation. So this, where we have a corollary. So every F algebra, so in other words, unital F algebras can be represented as F subalgebras of C infinity K spaces. So in some sense, I don't know, when I thought this, my reaction was, well, then the concept of an F algebra is artificial. Why do we need to define F algebras if they are nothing but subalgebras of C infinity K? There is a kind of, it's more historical reason that much of vector lattice theory comes from the Dutch group, comes from Zaanen and his students. And Zaanen was a constructivist, so he did not recognize the axiom of choice. And most people from his school, they do not believe in the axiom of choice. And therefore, they don't believe in representation spaces. So this Crane-Kakutani theorem, Maeda-Ogasawara theorem, for them, this is heresy. So they don't use them. So much of what I presented in my talk today would make no sense for those people because, well, I use the axiom of choice.
Yes. It's like we in our faculty, we say to students, when you pass a chair of mathematical logic, don't say axiom of choice. Otherwise, they will jump out of it and attack you, etc.
Yeah, well, and so there is a big chunk. So what I presented, if you go and look at the literature, much of what I presented today, in the literature, you will see very, very long and very technical proofs of those theorems, avoiding representations and avoiding the axiom of choice. So pretty much all that I showed you today can be done without using the axiom of choice, but the price is that proofs become very long and very technical.
Yeah.
Okay, so the last portion of my talk is about disjointness preserving operators. So the definition is very natural. It just said that T is disjoint. So if you have T from X to Y, so T is disjointness preserving if X disjoint with Y implies Tx disjoint with Ty. So it's a very simple definition. For some reason, somehow for a long time, I didn't find it natural until I realized that you can actually restate it in terms of one element. Equivalently, for every X, the modulus of Tx equals the modulus of T of the modulus of X. Okay. So that's this way you can restate the definition using only one element rather than two. And this is a large class. This class includes all the previous classes. So recall that we had this for band preserving, recall that band preserving have this property that X disjoint Y implies X disjoint with Ty. So we can put T on one side, but then we can iterate this. So then definitely if we just repeat this, then we have, this implies Tx, Ty. So band preserving implies dp. So this is definitely a larger class. So this dp includes orthomorphisms. And central. Well, another important class that it's actually, this is an easy exercise, that for a positive operator, for a positive T, T is disjointness preserving precisely when T is a lattice homomorphism. So T is a lattice homomorphism. Lattice homomorphism means it preserves lattice operations. And well, on the one hand, this is a good news. It says that DP operators are really, it's a very natural class. But it also gives you a bad news. It means that DP operators don't even form a subspace. So the set of all DP operators doesn't have any good structures because so DP operators do not form, like for orthomorphisms, we prove that orthomorphisms and central operators, they form a vector lattice. But DP operators don't even form a vector space. And the reason is very simple. Let's consider CK. Take X, so let's do this example. Take X to be CK. Then we know that on X, if we consider real valued orthomorphisms, so for a function, for a functional, so F is a lattice homomorphism, if and only if it is a point evaluation. Dirac measure, just Dirac measure. So lattice homomorphisms are precisely the Dirac measures. But if you take two Dirac measures, if you take delta S plus delta T, if you take 2 points S different from T, then this is not a Dirac measure anymore. So this is no longer a lattice homomorphism. Well, so the sum of two disjointness preserving operators need not be disjointness preserving. So this example shows that the sum of two disjointness preserving operators need not be disjointness preserving. Because for positive operators, we know that lattice homomorphism and disjointness preserving are the same thing. And now disjointness preserving operators have some nice properties, especially if we throw in order boundedness. So let me combine this. Let me combine this in a theorem. So for an operator from T to X to Y, the following are equivalent. So first, T is disjointness preserving and order bounded. Second is that modulus of X less than or equal to modulus of Y implies modulus of Tx less than or equal than the modulus of Ty. So it is kind of monotonicity with respect to the size. So this operator is monotone with respect to the size of vectors. And 3 is that the modulus of T exists, is a lattice homomorphism, and it's computed pointwise. So it's kind of those operators whose modulus is a lattice homomorphism. And now, well, okay, I want to mention another interesting fact about DP operators. So if T from X to Y is disjointness preserving, order bounded, and invertible, then the inverse is again disjointness preserving. And order bounded. And in this case, the modulus of T inverse is T modulus inverse. So these two operations are interchangeable. Well, now a question that you should now ask, this question should come naturally. When we talked about central operators and orthomorphisms, I immediately showed you a functional representation for those operators, that orthomorphisms and central operators are essentially multiplication operators. Do we have something of this form for disjointness preserving operators?
Yeah.
Well, okay. Let me start with the good news theorem. That let's say in the special case of CK spaces, so consider an operator from CK to CK or CL. So let's say T is a continuous operator, just norm continuous operator between CK spaces. So then T is disjointness preserving precisely when T is a weighted composition.
No, in this case, yes.
So T is, well, MW composed with C phi. So TF is W times F composed with phi. And here W comes from CL, and phi is a map from L to K, which is continuous on the support of W. Well, then you can naturally ask this question. Okay, in the case setting of CK spaces, we have this. Can we extend this to C infinity K? Can we do just as we did before? So here is my big question. So suppose we have an operator. So let T be an operator from one vector lattice to another. So let's say it's disjointness preserving and order bounded. Okay. And let's say we apply Maeda or Gassavara, so we embed this X into some C infinity of K, we embed Y, so this should be K. We embed Y into C infinity of L. So conjecture,
Yes.
well, it's not my conjecture, but conjecture, can we represent T as a weighted composition operator?
Mhm.
Just as before, but now we can take, so T would be the restriction of some MW C phi, restriction on X, where W would be in C infinity of K, of L, and phi as before. And unfortunately, in general, this conjecture is false.
Mhm.
False in general. But it is true under various mild assumptions.
Mhm.
So, for example, it is true under it is true if both spaces contain the constant functions.
Mhm.
Well, here I should, to be more formal, this is the constant function of K, and this is the constant function of L. More generally, if the range of T contains a weak unit of Y, even more generally, if range T is contained in the band generated by the image of a single element. Well, this, in particular, this is satisfied if there exists U in X, which is a quasi-interior point, which means that the ideal, if X is a Banach lattice, sorry, I should say, if this is a special case, if X is a Banach lattice with a quasi-interior point, And this means that there exists U in X such that the ideal generated by U is dense, norm dense in X. Well, really, this is the key one. All this, the other three conditions actually follow from this one. And now there is another condition which kind of goes in a different direction if T is order continuous. So all these conditions guarantee that T can be represented as a weighted composition operator. And well, I am definitely not going into proofs, but I would like to mention a couple of a couple of tools that I used in the proof that I think these tools are of independent interest. Okay, just, I need an extra page.
One second. No.
Okay. Okay, so let me just, so there is a theorem, one ingredient. This is a theorem due to Abramovich, Aronson, and Kitover. They have a book where they studied these issues with modules. So they would replace CK spaces with CK modules, which I'm not really an expert, but for some people here may be of interest. But they say that under the assumptions, so what they proved that if you have such a situation, so T is an operator from X to Y, dP, order bounded, and then you embed X into C infinity. Oops. You embed C infinity of K, you embed Y into C infinity of L, so under the same assumptions. So then we can actually write T as M times W, so there exists W in C infinity of L, such that T can be written as multiplication modulus of T followed by the multiplication by W. So this is a kind of a polar decomposition. So you can write T as a composition of a lattice homomorphism and the multiplication operator. So we are kind of almost, so now this essentially reduces, because we know that the modulus of T has to be a lattice homomorphism, this reduces the question to lattice homomorphisms. Because we know that the modulus of a dP operator is a lattice homomorphism. So now all we need to do is to show that this is C sub phi. And the other important ingredient is a lemma. Well, it's not a theorem, it's usually called Hart's lemma. This is due to Hart. Under the same assumptions, well, almost slightly stronger. So again, suppose T is an operator from X to Y. So T is disjointness preserving and order bounded. And I will make one extra assumption that X and Y are order complete. Then there exists and again, I represent X inside of C infinity K, Y inside of C infinity L. Then there exists a lattice homomorphism S from CK to CL, such that if I apply T to a product, you see now I'm using products, where F comes from, so G comes from X, but F comes from CK. If I multiply by a continuous function, this would be S of F times T of G. And kind of motivation for this, if we already know that T is a weighted composition. Then what we would have in this case? Then if I apply T to Fg, well, this would be weight times F times G composed with phi, but I can now rewrite this as F composed with phi times W times G composed with phi. So this is exactly F composed with, this is C phi F times TG. So that's where this Hart's lemma, the heart of Hart's lemma comes. But again, proving Hart's lemma requires some technical work. And then even after that, proving from Hart's lemma, proving all these statements that I listed here, it still requires some work. So definitely cannot be presented in a talk. But I think this is the nice point for me to stop.
Okay, thank you very much. We're on distance we applaud. And what about questions? Anar,
I have a question, yes, please. Well, in your representation of a unital F algebra into C infinity K, what's going to happen if your algebra is L infinity of K, something like von Neumann, commutative von Neumann algebra? Do we have some real formula how it's acting there?
No, I didn't get the question. Okay, so we have an F algebra. So you are talking about this.
Yes, your corollary.
Yes, that every unit F algebra can be represented as an F subalgebra of C infinity K. Yes.
So what can happen if X is capital L infinity of K, for example, for some measure, for some positive measure?
Well, you can represent.
Formula?
Well, this is even better because capital L infinity of a measure space.
Yes.
It's an AM space, so you can actually represent it as CK space.
Yeah, that's right. Do we have a formula there? Oh, yes, you can do. It's the same, right?
Yes, it's the same.
Okay. I see. Okay. So your theorem is okay.
Okay, other questions?
Well, I have a question which is maybe is not directly related to your talk, but is somehow inspired by your talk. I mean, the picture at the top of the last page, where you embed X into C of K and Y into So the question is, do C of K spaces, or maybe C infinity of K spaces, do they have some injectivity type property in a suitable category of maybe vector lattices or something like that? So maybe if you have such a picture, can we try to extend T to an operator between C infinity of K and C infinity of L?
Well, I don't know. I am sure that this has been studied. I know that there are many people in vector lattice community who are interested in this kind of question. So this is certainly known, but I don't know. So I never thought of this, and I don't remember the answer. So my guess would be that probably not. But it's a guess. Infinity.
What are injective objects and what are projective? Maybe Timur Oikberg has something.
Yes, Timur would, but I don't know. Timur may not be interested in C infinity spaces because they're not Banach lattices.
Nevertheless,
you cannot put a norm on C infinity K. There is no good norm on it.
Yes.
So it would really, you have to be in the category of vector lattices. So your question is, are these injective objects in the category of vector lattices? And
but let's try to be broad-minded. Okay, so if there are no questions, let us thank the speaker for a very interesting, creative, and very well organized talk. Thank you very much. And let me remind that our list of Troitskys is not fulfilled. The next will be Zhenya. Now Volodya will be Zhenya. and it will be in 6 o'clock as usual. So, Volodya, it creates some problem for you, but let's hope.
Well, I can watch it later in the recording.
Yes, exactly. So, we'll see everybody next week, next Friday. Thank you very much. Bye.
До свидания.
Спасибо, до свидания.
Свидания.